All right, class. So this is, I'm going to do a little kind of a quicker, well, we'll see if it's quick, but this will be the first, your first lesson in Calc BC, so let's see how it goes. So what we're going to talk about today are limits, which is something that you probably should have discussed in pre-calc right at the very end, but you probably didn't go extremely in depth into it. So we're going to cover this a little bit more in depth here. Limits are actually kind of interesting. It's kind of where everything in calculus, everything we're going to define this entire year in calculus will all come back to being defined as an actual limit. So in any case, students generally dislike limits, but in fact, limits are an integral part of calculus and is really just like the base of calculus. So yeah, let's talk about limits. And I'm going to give you an official definition. It's not something that you will see on the AP exam, but it's good to kind of understand what the official definition is. Okay, so let's say you have a function. So we'll say the function f, right, has a limit of L as x approaches c. In other words, the limit of f of x as x approaches c equals L. If and only if. IFF stands for if and only if. Okay, so if and only if given epsilon greater than 0, okay, so any number epsilon greater than 0, there exists, that means exists, there exists delta greater than 0 such that for all x the difference between x and c, absolute value, so it's got to be positive, is going to be less than delta. This implies that the function, the difference between the function and the limit, is less than epsilon. Okay, this looks really confusing. So first off, let's read this again. All right, so the function of f has a limit of L as x approaches c. In other words, that's this statement right here, right? The limit as x approaches c of f of x is L, if and only if, given any number epsilon, which is greater than 0, there exists a delta, which is also greater than 0, such that for all x, if the distance between x and c is less than delta, implies that the distance between the function and the limit is less than epsilon. Basically, what happens is, like, in a sense, what's going on is it's like a game, okay? And the game is, I have this function, right? So I have this function. Let's say I have this function, and you say, okay, I give you this delta number, and this delta number is really small, okay? Let's say we'll just go with 1, okay? So if I say, the game would be you give me an epsilon, which means I need to get the function and the limit to be closer than epsilon. So if you give me 1, I want the distance between the function and the limit to be less than 1. Okay. In other words, let's see here. Let's see if I can graph this. Okay, so let's say here's this function. All right. And let's say right here, that's C. Okay? And we're saying that's L. So as our x approaches C, our function approaches L. That means the limit of our function has to, as x approaches C, is L, right? That's what we're saying. Well, this is true if when you give me an epsilon, let's say you give me epsilon equaling 1. That means that this right here is 1 less than the limit, and this up here would be 1 greater than the limit, right? So this right here, this distance right here is epsilon. Okay, so we got epsilon on the top, epsilon on the bottom, so it's a distance, right? So here's our epsilon. So epsilon up and down, right? So epsilon, that's the distance. Well, you want me to be inside you want my function to be inside that range, okay? And I say, okay, well, if you want the function to be inside that range, I have to be able to come up with a delta that guarantees it, right? So I can say, well, the delta can be right here. Right? So that delta, so notice the function is inside this range as long as my x value is inside this domain. And if we can continue to play this game, then the limit exists. Let me give you an example that's numeric. So let's go with, all right. Here we go. I'm going to give you a okay, let's take f of x equaling 2x plus 4. All right, and my claim is that the limit as x approaches, let's say, 3, okay? My claim is that as x approaches 3, the limit of f of x is going to be 10, right? As I send x to 3, this function is going to go to 10. So if I were to graph this, 1, 2, 3, 4, 1, 2, 3, 4. We have this function, right? So as I approach 3, here's 3, and here's 10. Okay, so is it true that no matter what epsilon you give me, I can give you a delta in which, as long as the difference between x and c is less than that delta, I have to be less than whatever epsilon you give me. So let's say you give me an epsilon of 1, okay? Well, if you give me an epsilon of 1, that means that I need the function. I need this function, right? I need this function to be less than 11, but greater than 9. Does that make sense? Right? The epsilon has to be the difference between the function and the limit. And since I'm claiming the limit is 10, that means go 1 up from my limit and 1 down from my limit. So my function needs to be in between 10 and 9. Well, how can I guarantee that the function's in between 10 and 9? Well, I can guarantee that the function is going to be between 10 and 9 as long as what would be my delta? Well, basically, so if my delta was 1, let's just guess, right? So let's do 1/2. Let's go small. So if my delta was 1/2, that means my x must be less than 3 1/2, right? Which, so 7/2, but greater than 5/2, right? So as long as I'm in between these two things, my function's going to be in between these two things, right? And that's pretty easy to check. If I plug in 5/2 into here, it's going to be 5 plus 4, which is 9. So I'm going to be in between 9 and 7, exactly the same thing, right? So as long as I go from 5/2 to 7/2, we're good. And in fact, no matter what you choose for epsilon, we can always do exactly half of it and get it, right? So if you say, well, actually, I want my epsilon to be, let's say, 1/4. I want you to be within 1/4 of the limit, which means, you know, my function needs to be less than 10 1/4, while it also needs to be greater than 9 3/4, right? Okay, that's where my function needs to be. Well, what sort of delta do I choose? Well, the delta I choose is actually going to be 1/8. In other words, my x, so 3, right? So my x is going to be less than 3 1/8, which, by the way, 3 1/8 is 25/8, or it's going to be 2 7/8, which, by the way, is 23/8, right? And if I do that, I'm going to actually get my 9 3/4. I'm going to get my x to be inside that, right? So basically, you give me a range. So as long as you give me a range and I can give you a domain so that my function is always inside that range, then this limit exists. So hopefully that kind of makes sense. I can go over this again in person if we want, but that's sort of the real broad idea. So this, by the way, I know that took a little while, but this is the definition of what a limit is. You will never have to prove that a limit exists using this official definition. You're going to have to just, solve for limits and prove that it exists using other methods. So don't worry, but this is the official one. If you choose to be a math major, they might ask you to do this in college, but luckily they took it off the AP curriculum quite a while ago, actually, maybe 10 years ago. I had to do it when I took AP Calc, but you don't, so lucky you. In any case, all right, so I'm going to stop the video now and upload it, and we'll kind of continue on with some other stuff later. Anyway, all right, so that's the definition of a limit. Thanks.